Okay, in the last video, we looked at the derivative of the exponential and the antiderivative of exponential functions. Now let's focus on the log function. This proof is great. We want to know the derivative of this, okay? So this is a nice nifty proof here. You're going to love this one. Okay, so remember, if y equals the natural log of x, then that means the equivalent exponential function is what? Do you remember? That is, the input becomes the output, and the output becomes the input because there are inverses of each other. So those are equivalent statements. One's log form, one's exponential form. Okay, so what we do in math all the time is I want to know what f prime is, right? I want to know what the derivative of the log function is. So what I'm going to do is rewrite the log function in this exponential form and then and then use the fact that I know what the derivative of e to the x is and e to the y in order to establish the derivative. So stay with me here. It's not, I wouldn't be able to expect you to do this on your own as a Calc 1 student, but you should be able to follow this. Okay, so it's you might not think to rewrite it as x e to the y, but the steps should make sense. So let's see if they do. So now I'm going to take the derivative with respect to x of both sides. Derivative of x is 1. Now, what is this? This is implicit differentiation, right? So with implicit differentiation, how do you do this? And by the way, I mentioned this. I'll start talking about the final a little bit again. If I give you an implicit differentiation problem, it's almost definitely going to have exponentials and logs, right? That's the idea of the final. Like, I've already asked you questions on all the other functions, so the final will be kind of the same questions, but it'll be heavy on log and exponential function. That is, I'm going to ask you to do a lot of derivatives. I'm going to ask you to do a lot of integrals, but you're just going to see the exponential function and the log function a lot more than any other functions, okay? All right, so let's see. Where was I? Derivative of x is 1. Derivative of e to the y with implicit differentiation is, because e to the x is its own derivative, then it's e to the y times the derivative of the input function, where the input function is the exponent, always with the exponential function, right? If it's e to the something, derivative of e to the x is e to the x. Derivative of e to the u, or e to the any function of x, is e to that function times the derivative of that function, the exponent. Okay, so the goal here, let's solve for dy dx. I get 1 over e to the y. And I say, well, wait a minute. I'm trying to find the derivative of the natural log function. So I can go back and substitute, because x equals e to the y, right? So e to the y is just equal to x. And then we've found dy dx right here, right? Remember, I know we did a lot of substitution. Y is still the natural log of x. Right, so in the end, after the substitution, we ended up with dy dx, which is derivative of the log function, and when we back substitute, we got 1 over x, and we are done, which is another very interesting result. Okay, the unique thing about the exponential function is its own derivative. The unique thing about the logarithmic function is you've never seen this before. Any derivative of a rational function was a rational function. But now we have this logarithmic function whose derivative is a rational function. Okay, so the derivative of the natural log of x is 1 over x. Now, can you fill in the blank for this one? I'm going right to the chain rule. The derivative of the natural log of u, where u is a function of x, is what? You should be able to fill this out. It's 1 over u times the derivative of u, right? This is the easy version. This is the chain rule version. Let me do the exponential one just so it makes sense, a little more sense, hopefully. Derivative of e to the x is e to the x. The derivative of e to the u with respect to x, remember that u is a function of x, is e to the u because of the derivative of the exponential function times u prime, or du dx. 4 new rules. Okay, let's continue that list. The Antiderivative of e to the x is e to the x. Okay, now I don't really have one for, I'm not going to do this because these really depend on you. Like if I give you one of the function of x that is indeed the exponent, okay? So there isn't officially a rule because there has to be like, I mean, I guess you could have, you see some textbooks like this, right? If the derivative shows up here, then if the derivative shows up in the integral, then the antiderivative of e to the u times u prime would just be e to the u plus c. For example, e to the 2x times 2 dx, and that 2 would usually be in front, would just be e to the 2x plus c. Because I know if I differentiate it, I'll get that 2 back. Okay, so you might see this, I mean, this is kind of, I don't like this formula, because when I give you these functions, we're just going to let u be this. It doesn't always work out this nicely. There's often another like constant hanging out. Like what if this was what if I asked you to put like this was 6? Right? Then you can still do it by doing u substitution, letting u be the exponent, but it doesn't work out like perfectly. Okay, so I won't really have a formula for that, but I'll have a method. And the method will almost always be to do u substitution and let u be your exponent. Okay? And we're going to do a bunch of examples. So what did we learn about this guy? Well, I actually can make this a little bit stronger. Remember, we have this property for the log function. This domain is just positive numbers. We didn't have that issue with e to the x, so I didn't have to worry about it. So instead of saying, oh, I can only apply this derivative property if x is positive, I can do better than that, actually. I could just say, well, I'm allowed to. It'll work out. And we would need a separate proof for this, because the proof I did was dealing with an x which is only positive. But we could do it, and we could establish that even if that I can change my natural log function so it incorporates negative values. That is, the natural log of anything negative would still work out. You'd still get 1 over x over here. Okay, so that's why you'll see this. So in other words, this makes it a little more powerful that we can indeed have the derivative natural log of a different function, absolute value of x. Okay, and that will also help us when we integrate. So look at this function. What's the domain restriction for 1 over x? It's not positive values. It's just x can't be 0. Right? So if we weren't able to include those absolute value bars, then we'd have a real restriction on our result of integrating 1 over x. We could only, if this were our formula, x could only be positive. But we'd rather be able to integrate a function that has negative x values, and we can by including those absolute value bars. Okay? So notice this is the real interesting piece. I said the derivative of e to the x, and I gave you a formula. I said the antiderivative of e to the x, and then we had a formula. But with the log function, it's different, right? I say the derivative of the natural log of x is 1 over x. So the derivative, or the antiderivative, I'm not giving you a formula. This comes later. This is actually more complicated. You don't have a formula in Calc 1 for this, right? I don't know what that is yet. But I do know what the antiderivative of 1 over x is, because I know what the derivative, that is indeed the derivative of the natural log. Okay, so that's just the antiderivative, right? It's a good word. The antiderivative of 1 over x is natural log of x, because the derivative of the natural log of x is 1 over x. Okay? Okay, good. Now, my next question for you would be, what are the chain rule? Anytime you learn a new rule, you got the chain rule for free. Okay, so let's see. We got, I mean, this is really one rule here, right? That's one rule. I see that as one rule. The derivative of x, e to the x, and then there's a chain rule version. Same thing for this. I know what the derivative of the natural log function is. So I know what the derivative of the log function chain rule version, we could do that. Okay. So integrals. So we got two more. Now, what's the chain rule version of that? Well, I already talked about e to the x. You could, I'm curious to see if this textbook does it. It probably does. That is, if you have, and I don't love this one. Right, this is the chain rule equivalent of this. The reason I don't love it, and I'll explain this when I do an example, is that you're hardly ever given exactly e to the u times u prime. It's most of the time e to the u times some multiple of u prime. But you can still do it, right? Because if it's just a constant multiple hanging out here, then like if there's a 5 here, then the 5 comes along for the ride. No big deal. Okay, so that would be, I mean, integration is just always more complicated than differentiation, and that's one piece of it there for these formulas. So can you do the same thing with the log function? Well, it'd have to be what? 1 over u, and then times u prime, and notice this looks weird because the variable of integration is u, but you're integrating over x, that's what the dx is referring to. But just remember, u is, I mean, you could, if you wanted to, use a function of x. Always a function of x. So the variables do line up there. Okay? So you will see this one. I guess I should talk about it. Like I said, I don't love these because it doesn't always work out like this. I mean, it hardly ever works out like this where you're just given u prime over u. So I'll show you my method for integrating. I got to do a bunch of examples of these, and I'll show you how I tackle this. I don't like memorizing formulas. I like knowing the process, right? But this would then be what? The natural log of u plus c. Okay, so let me show you that one. Let's start with that one. So if I say, tell me the antiderivative, my first integral in Calc 1 class for that results in a natural log function. Okay, let's do it. So if I said 2 to the x squared plus 1 dx, and I'm going to give you another example that's very similar, and I'll say 6x over x squared plus 1 dx. Okay, if you have all your formulas memorized, you say, well, wait a minute. By the way, this one you would see 1 over u times u prime would be the same thing as u prime over u. Right, so you'll see this often in your textbook. U prime over u, natural log u. So if you recognize this, look, I don't even have to do any work. And this is totally acceptable. Right, if you didn't show me, like I always make you show work on your paper, right? But that's all the work you need to do because you recognize that's u prime over u. And the antiderivative of u prime over u is the natural log of u plus c. Okay, so that's fine. But I won't do that anymore. I'll always use my u substitution method. Because yes, it might work if I recognize it's just pattern recognition, right? That's all we need to do for that one. However, it's not always easy to recognize those patterns. So in general, when I'm given a quotient, now remember, we haven't integrated quotients, right? We have a quotient rule for differentiation, but we haven't really got one for quotients. But now we do, right? And it's only for the log function. In Calc 2, you'll handle more complicated quotients that'll have different options, different formulas. For right now, it's mostly the log function. Okay, I think I gave you, like on your quiz or something, I give you like something like that, and then you say, well, wait a minute, that's a quotient, and it is, but remember, you can simplify it so it's not a quotient. That's really the only thing we've integrated so far. Okay, so back to this one. Here's my method. So remember, I'll put a star, big star. I'm always going to let u, remember we do u substitution, u is always the input of my composite function. Well, now u is going to be my denominator, right? That is not a composite function. I mean, you could think of it as a composite function, 1 over x, but just there's no operation on that denominator. So the general rule will be to let u be the denominator and then go from there. I solve for dx. And then I do my substitution. So I do 6x, the denominator is u, dx is du over 2x, and this fixes my problem that I didn't have exactly the derivative up top. 6 over 2 is 3, and then I get 3 times 1 over u du. I I integrate and I'm done.